I'm not sure which Brian you're referring to, so if it's a compliment, I'll take it. If not, it's
okay. All right. First disclaimer: I have a little bit of a cold, so I stayed home. So this is part 2 of Brian Dennison, who's going to talk to us about the evolution of the universe.
This is the tree part, I guess. A few loose ends here. Today I brought with me an asteroid, or a piece of an asteroid called a meteorite, a rock that fell out of the sky and landed in Siberia. It's an iron meteorite. First, we'll let the Zoomers get a look at it. Sorry, that's, you don't get to handle it, but there it is, an iron meteorite. It's pretty dense because it's iron, probably some nickel as well. And the surface is that way because of entry through the Earth's atmosphere. And I'll just pass it around.
All right.
There you go. Cool. About 10% of meteorites are iron. So that's in that 10% category. And now I'll go ahead and switch over to slides. As we do that, can everybody understand me okay? The audio is good. Okay.
Audio is good. Good.
Okay, good. So
let me get the screen sharing going.
Brian,
yeah,
aren't those worth quite a bit of money?
It depends on the type. It depends on the mass.
Wow.
So that's not worth a huge amount of money. But if it were this big, it'd be worth a lot.
Yeah.
Yeah.
Yeah. I guess. Yeah.
I'm not even sure. I'm not really a meteorite expert.
Yeah.
And
You
so
kept your solid gold one at home.
I can't bring that. But that's the only meteorite I own, I think. Anyway,
You'll admit to in public at least.
then I'll admit to the others. I can't talk about where they came from, but anyway. So just a few loose ends here, real quick. Last time, David asked me how long those pillars are in light years, and I didn't really know the answer, and I made the mistake of trying to answer it when I didn't know the answer. But I looked it up, and they're about 5 light years long. Okay, and those are star-forming regions. And let me just put that in context. This is where they're found in a larger structure called the Eagle Nebula. And if you look right in the center, you'll see the pillars, but you see their surroundings. And this is a huge star-forming region. And in fact, in the center of this region, so many stars have formed that their light, in particular, their ultraviolet light, has hollowed out a huge cavity. And the pillars find themselves right in the middle of that cavity. And eventually, ongoing star formation will heat up the whole thing. The cavity will consume the entire object. And the gas in the cavity is about 10,000 degrees Celsius. And that will put an end to star formation in that particular region in our galaxy. Okay, we also talked about stellar death last time. So, David, does that sound okay? The answer to your question? Okay.
Yeah. Yes, thank you.
We also talked about stellar death, and I want to add to that just a little bit. As I said, this is the eventual fate of the sun when it blows off its outer layers after it has been a red giant. Its core becomes exposed, which contains a substantial fraction of the mass of the sun right at the center of the image. Of course, the Zoomers can't see my pointing, so I'll try to describe things as best I can. When the sun is a red giant, that will happen because it will run out of hydrogen fuel, and its core will be mostly helium. But the core compresses, the envelope expands, it becomes a red giant. And when the core compresses, it becomes so hot, it actually starts burning helium, the prior waste product, into carbon. And so it finds a new way to supply itself with energy. But soon that new fuel of helium is exhausted. And when that happens, the core collapses, and this is what ensues. And you end up with a dead star called a white dwarf and an expanding envelope that's been blown off. Okay, so that's the way the sun will die. And the important point is that when this material is blown off, it includes helium and carbon. which have been processed by the nuclear reactions. And this is called enrichment because these heavier elements, helium and carbon, are now blown out into the galaxy where they will be incorporated into new generations of stars and new objects. Carbon is very important because carbon has the unique chemistry that Jeff will talk about that is absolutely necessary for life as we understand it. And all the carbon in our bodies, all of it, came from the interiors of stars. It was manufactured in stars through nuclear reactions. More massive stars have a different, do I hear a question out there in Zoom land? Apparently not. More massive stars undergo a more violent death, but they too become red giants. And here's one we talked about, Betelgeuse in the constellation Orion, which will probably explode anytime in the next 50, 100,000 years.
Anytime.
More massive star than the sun, and it, like the sun, finds a way waste product and to get more energy from nuclear reactions. So Betelgeuse has probably burned helium into carbon, but it can keep going because it's massive. It has the necessary density and pressure at the center and temperature to burn carbon into heavier elements like nitrogen and oxygen, magnesium, silicon, all the way up to iron. All of those, there's a sequence of many reactions which fuse light elements into heavy elements and release energy. And by releasing energy, it sustains the star. But when it gets to iron at the core, iron cannot be burned in nuclear reactions in a way that releases energy. So the core collapses catastrophically, blowing off the outer layers. The result is called a supernova explosion. And I mentioned last time that these are fairly rare events in our galaxy. One was seen in the year 1054. The precise position in the sky was recorded by observers in China, the Middle East, the American Southwest, not Europe. We don't know why. I'll leave that to the historians to figure out. But the observers in China, what they really saw, and I did mention this last time, was what they called a guest star. It was the appearance of a new star to them, where previously they hadn't been aware of one. And so they recorded the position of the guest star very precisely. They knew it was important because it was so bright it could be seen in the daytime for a month. Wow. Okay. So we were given, not this diagram, but the information that's in this diagram. We were given by ancient observers the precise position of where this occurred. And when we looked there, as we saw last time, this is what we found. It's called the Crab Nebula. It's the expanding remnants of that explosion. And most importantly, it contains carbon and silicon and oxygen and nitrogen and magnesium and iron and a whole bunch of other elements that are being blasted out into the galaxy. And those are the ingredients for building planets, for example. So the Earth has lots of magnesium and iron, silicon. Rocks are been part of silicon. And all of that was formed and released in supernova explosions.
And God said, let there be oxygen, and he said it was good.
Let there be oxygen. And then, interestingly enough, oxygen wasn't present in the original atmosphere of the Earth. But that, I'll leave that to Jeff. Okay. So the other thing I want to point out is that right smack at the center of this nebula is the original core remnant of the expansion. It's called a neutron star. The core contracted under gravity to a volume about the size of Washington County. And it carried with it into that very small volume a couple of an amount of mass equal to several times the mass of the sun. So it's an unbelievably dense object. It's called a neutron star because it is literally a glob of neutrons held together by gravity. And if I wanted to try to achieve that density on the Earth, which I can't, fortunately, I would have to go and take the mass of Roan Mountain and compress it into a volume of about a cubic inch, about this cap on this bottle. Okay, that's the kind of volume you have, or the kind of density that exists in a neutron star. Okay, so last time we had moved out beyond the Milky Way and encountered the nearest major galaxy to our own, the Andromeda Galaxy, 2 million light years away. So we're seeing it the way it looked 2 million years in the past. Also in our neighborhood, we have another spiral galaxy called Triangulum. It's a little smaller than our galaxy. The Andromeda Galaxy is a little bit bigger. We're looking about 2.7 million light years away now. These galaxies, these spiral galaxies, have at their centers supermassive black holes, like the Milky Way does. We don't know how they got there. It's a big open question right now. Working our way out farther, we find this spiral galaxy, 21 million light years away. It's called the Whirlpool Galaxy. So 21 million years in the past. If you want to see what it looks like now, you'll have to wait 21 million years. I will double the distance, jump out to 40 million light years. The picture quality is still good considering the distance. And this is another spiral galaxy. Their orientations in space are completely random. So once in a while, we'll see these things edge on. Okay, so this is called an edge-on spiral. And you can see that dark lane through the middle, consisting of gas and dust, and that is the material that forms new generations of stars. Okay, by the way, and if you look at an image like this, or almost any of the images, you'll see a bunch of stars. And those stars are stars in our galaxy. Those are foreground stars. So it's kind of like you're looking through a window pane, which is a little bit dirty, at a mountain scene miles away. And the dirt on the window creates little specks right up in front of your eye, or kind of like my glasses, which I haven't cleaned lately. And those are just local stars nearby in our own galaxy, maybe 100, a few hundred light years away. Yes?
Are the photos you've been showing from the Webb telescope?
Not yet. Well, two of the previous ones where I did the quick recap were from the Webb, but these are from ground-based telescopes.
Thank you.
And I do have some Webb images. Here's another spiral galaxy. Now we're out 61 million light years. It's called a barred spiral galaxy. And in fact, our own Milky Way has that bar in the middle. Now, it's very important to remember when you see these images, to remember that the bar is not solid. The arms are not solid. Those are all stars that are orbiting around the center, and their collective orbits create a pattern. And a lot of work has been gone into understanding why that pattern is there. Here we're looking back, what I say, 61 million light years. 66 million years ago, the dinosaurs and many other life forms were wiped out by the impact of an asteroid on the Earth. Okay, so we're looking almost back to that time. Here's another galaxy. This is from the Webb telescope. This is 46 million light years away. And the Webb telescope operates in the infrared. So it uses different infrared bands. And in order to render a seemingly color image, false colors have to be assigned to those infrared bands. And to really scientifically interpret the image, you need to know what colors were used for what infrared bands. But still, it makes a nice, pretty image. And you can see in the infrared through a lot of the dust and see what's going on. And some of the bright regions are regions of intense star formation. And you'll also notice, if you look carefully at the image, you'll see some cavities. In fact, if you really look at it, there are dozens, maybe even 100 cavities. And those are places where young stars formed. They develop very strong outflowing gas called winds that evacuated cavities, or if you will, they blew up bubbles. Sometimes these are called bubbles. And the gas that's in those bubbles is about 1 million degrees. There are bubbles in our own galaxy, but the process of finding them has been painstaking because we live in the disk of our own galaxy. Okay. Now, from these slides, you would think all galaxies are spirals, but they're not. There are different types. And there's a whole category that can't be categorized. They're called irregular galaxies. And this has been classified as an irregular galaxy, but what it really is a pair of interacting spiral galaxies. Two galaxies that have come into close proximity, and the gravity of one affects the orbits of the stars in the other, and vice versa. Often these result in mergers. The final result is often a much bigger galaxy. We know that our own Milky Way has grown by consuming the stars from smaller galaxies that have ventured into its neighborhood. In 5 billion years, the Andromeda galaxy will collide with the Milky Way galaxy. That's about the time the sun will be running out of fuel. Okay, and when this happens, we think those two galaxies will merge into a much bigger galaxy. This is part of the process by which galaxies evolve. But then there are other kinds as well, which in my slideshow are grossly underrepresented. For example, now I'm going to test the system. It worked. Great.
There we go.
Yeah. This is called a dwarf elliptical. It has an elliptical shape, a little bit like a football, almost no gas and dust, virtually no star formation, but tens of thousands, hundreds of thousands, maybe even 1 million stars or more, sometimes as much as 1 billion stars. Most of the galaxies in the universe appear to be dwarf elliptical galaxies like this one. Not so spectacular to look at. Here's an elliptical galaxy, but a completely different type. This is called a giant elliptical. It has several trillion times the mass of the sun. So it's 10, 20 times more massive than our own Milky Way galaxy. And it has a nice symmetrical round shape. But you'll notice at the center of this has a name, by the way. It's called M87. I hate to mention catalog names, but I won't come back to that. It's a giant elliptical. It's 54 million light years away. The thing to notice is the very bright spot at the center. And emanating from that bright spot to the right is a jet-like structure. It's actually best described as a particle beam. It's energetic particles that have been accelerated by some process to a speed very close to the speed of light. And of course, many years of investigation went into understanding what was going on at the very center of M87 and what was creating the jet. And of course, the answer is now predictable in terms of what we now know about the universe. It is a supermassive black hole that lives at the center of M87. This one is about 6.5 billion times the mass of the sun, still a small fraction of the mass of the galaxy. You can't see it in this image because it's way, way too small. But material that falls into that black hole releases huge amounts of energy that get funneled into a jet that we see here. Now, the material coming out of that jet eventually gives off all kinds of emission that attracted our attention to objects like this. We now have a picture of the black hole at the center. And this was taken with an array of radio telescopes spaced all over the Earth. And here it is. This was actually the first picture ever made of a black hole. This is at the center of M87. Of course, you're not really seeing the black hole except in silhouette. You're seeing the gas that orbits the black hole becomes extremely hot, gives off a lot of light as it's falling into the black hole. And the black hole is the hole in the center of the donut in this image.
Brian,
Yes.
I'm assuming the yellow is a cooler band of gas. How do you get like the cooler band in the middle of
The yellow, I think, is actually hotter in this diagram.
Okay.
And you also notice some stripes. And this was processed in a way to use polarized light, which I won't go into, which shows where the magnetic fields have been caught in this gas and is being pulled in. So they're very strong magnetic fields. It's not just matter that gets sucked in. And it manifests itself through those bright stripes in the yellow region. Okay, this black hole is, I think I said, it's about 6.5 billion times the mass of the sun. We don't know why it's there. But not all the matter gets pulled into it. A lot of it gets shot out. This is a very common phenomenon. It was first observed, or at least the results of it, were observed back in the 1950s and 60s with, for example, radio telescopes. This was, when I say was, because it collapsed, this was the largest telescope of any type on the planet, operated in northern Puerto Rico. I did a lot of my observational work down there in the 70s and 80s. And it collapsed on December 1st, I think 2020. And that confirmed for me that I'm glad I'm retired. It tells me if a telescope I use collapsed, that maybe it's my time to maybe not collapse, but retire. Okay. We used to observe quasars with this, and what we would observe is the radio waves coming from the jet and the material that gets shot out by the jet. And not just, we didn't see this in just M87, but in literally thousands of objects in the sky. Here's one such object. It's a quasar. Quasar means quasi-stellar object. And when people first looked with visible light telescopes at the sources of radio emission, what they saw was puzzling because they just looked like stellar images. It's marked near the center of that photograph. And it was very confusing what's going on here. In fact, what's going on is there's a supermassive black hole at the center. It gives off so much light that it overwhelms the light from the galaxy and makes it very hard to even see that. And this quasar has got the very interesting name of 1117 plus 14. Don't worry about that. It won't be on the final. It's about 4.1 billion light years away. And I find that distance interesting because the Earth is about 4.6 billion years old. So we're seeing that galaxy at a time not so long after the Earth formed because of the look back time. Well, if we look around, we find out the galaxies live in clusters. Here's a cluster called the Virgo cluster. It's 54 million light years away because it contains the galaxy we just looked at, M87, which is the giant elliptical in the upper left corner. But you can see some other giant ellipticals. You can see a bunch of spiral galaxies. There are also, of course, foreground stars in our own galaxy in that image. Back in the 1970s, when astronomers first started using X-ray telescopes, they noticed that clusters of galaxies were strong emitters of X-rays because the medium between the galaxies is pervaded by a very thin, tenuous, but very hot gas at a temperature of about 100 million degrees. And a gas that hot gives off X-rays. And the amount of gas that's in there typically exceeds the mass of all the galaxies combined. So I could call that a cluster of galaxies. Everybody does. But I could also call it a great big blob of very hot gas. And that would be an equally accurate description of what that is. Going farther out, we come to another cluster called the Coma cluster, 320 million light years away. Its overall radius of the whole cluster, bigger than the image that you see here, is about 10 million light years from one side to the other. Remember, a spiral galaxy is typically 100,000 light years across. And if you look at the image, you can probably find a spiral galaxy. That right there is 100,000 light years in size. It's probably a galaxy pretty similar to our own. Now, back in the 1930s, an astronomer by the name of Fritz Zwicky, Swiss-American astronomer, started measuring the motions of these galaxies because he realized these galaxies must be gravitationally bound to the entire system. Every galaxy must be moving in response to the collective gravitational field of the entire cluster. Okay, so they're in a sense orbiting around it. The time required to watch a galaxy move in this case, in the orbit, is way, way, way too long for anybody. But in fact, Zwicky was able to measure the Doppler shifts caused by the motion, because there's always the component of the velocity away from you and toward you. And of course, about half are moving toward you and about half are moving away. So he could figure out statistically how fast these galaxies were moving around. And the result was they're moving way too fast, because he could predict how fast by using all the mass in the cluster to try to predict the motions of the galaxies. And it was way, way off. Well, you say, okay, there's hot gas in there, you add that in. You do, and it's not nearly enough. And Zwicky called this a manifestation, first time 90 years ago, of dark matter, a form of matter that doesn't interact with light, a form of matter we can't see, it doesn't give off light, but it creates gravity. And so we infer its presence from its gravitational influence. And typically in a cluster like that, there might be 5 to 10 times more dark matter than there is luminous matter. This has been a mystery for like 90 years. Here's a James Webb image. It's called a deep field, and a long exposure looking into a piece of sky that is very devoid of foreground stars. There is one. If you see a star-like image with multiple points, those are diffraction spikes. They're manifestations of the telescope. They're, as far as we're concerned in this image, a little bit of a nuisance. But if you look, almost everything else in that image consists of galaxies. And if you look toward the center, there's a giant elliptical. In fact, toward the center, there's a cluster of galaxies. That cluster of galaxies is about 4.9 billion light years away. We're now looking back to a time prior to when the Earth existed. Okay. But there are other galaxies that are even farther away. There are spiral galaxies at great distances, but their images are frequently distorted because their light is bent by the gravitational field of the cluster of galaxies. That's the gravitational field of the galaxies, the hot gas, and the dark matter. And so, for example, you see really weird spiral galaxies that look extremely distorted. And that's because of gravitational, sometimes call it lensing. Sometimes the galaxy will appear twice. And that's because the light has found two paths to get to us simultaneously. So we get double imaging, we call it mirroring. So we get two images of a galaxy. Well, this provides a very powerful tool because if you can see the light from background galaxies, you can look at their distortions and infer how much mass is actually there. Not just the mass due to the visible objects, but the mass due to the dark matter as well. And so this is used to explore dark matter. Any questions in the room or in Zoom land? Okay.
And how big a patch of sky is that with all those galaxies in it?
Off the top of my head, I don't know, but I would guess it's probably something like a tiny particle held at arm's length. I probably should not make the mistake I made last time and try to answer a question for which I don't really know the answer, but I can promise you it is a really small patch of sky. Okay, that's the best I can do without having to go and look it up. Okay, here's another cluster. This is actually two clusters of galaxies. And the two clusters of galaxies are in the blue areas, one on the left, one on the right. And if you look carefully, you see the galaxies, they appear white. You see some giant elliptical galaxies in there, quite a few, in fact. And the blue registers the amount of dark matter. In fact, it registers the total amount of matter as determined from the lensing of background galaxies. So the blue is a register of how much mass is in that particular region. Okay, the red is an X-ray image. An X-ray telescope took the red picture. And here's the interpretation. That red is hot gas at 100 million degrees. It's in between the two clusters. Why? The reason why is because the two clusters pass through each other, a process that probably took 3-4 billion years. And when they went through each other, the galaxies kind of just glided right past each other. The hot gas, however, rammed into the hot gas from the other cluster. And as the two clouds of hot gas rammed together, they got stuck in the middle. The dark matter, mostly indicated by the blue, moved with the galaxies to either side. So this is some of the best evidence we have for the existence of dark matter in clusters of galaxies.
I have a question.
It's moving further apart.
Mm-hmm. They're both moving left and right, although we don't have enough time to see that motion because it would require billions of years. Somebody in Zoom land had a question.
I have a question. Has anybody fixed the photos and taken out the foreground stars?
No. And there aren't many. I see that one star with the really strong spikes. And a way you can tell how tiny a patch this is because actually there aren't many stars in it. And if you take a typical image of the sky, there's lots and lots of stars. And here we're kind of peeking between the stars, at tiny little patches of sky. But they have not, the stars, no attempt has been made to remove the stars. But right now, I only see one. So I'm not too worried about it. All those little tiny dots that you see, those are really distant galaxies.
Fascinating.
Yeah. There's 100 or a couple 100 billion stars in our galaxy, but we now estimate there's 1 trillion galaxies in the observable universe. And remember, every star in every galaxy has a bunch of planets as well. Okay. So we learned more about dark matter in the 1970s when the astronomer Vera Rubin started looking at the orbits of stars in galaxies. This is the Triangulum galaxy, pretty close to us. And Vera Rubin used the Doppler effect, to measure the motions of stars, orbital motions of stars around the center of galaxies like this one. And what she found out is the orbital motions of stars around the center was a whole lot faster than what would be expected from the visible disk. There it is. There you see the visible disk projected on this graph so that it scales with the horizontal axis in terms of distance. So if you just took the disk you can see and said, how much mass is in the disk and how fast should the stars be going? The answer would be given by that dotted line, typically 50 kilometers per second. But in fact, the speeds are actually given by the solid line. Those dots and error bars are measurements. So Vera Rubin was able to prove that the dark matter problem exists at the scale of galaxies as well. And she looked at other galaxies and more galaxies, and other people started looking at more galaxies, and they found the same thing. Most galaxies, if not all, sit inside a giant halo of dark matter. And our galaxy does, in fact. Okay. Any questions? Now we're going to back up and to about 1929, when Hubble used the Doppler effect. I don't need to explain the Doppler effect because we had a perfect explanation last Sunday. It was dead on. So we all know about the Doppler effect. I can skip that slide. And I'll show this a little bit complicated slide. It dates back years based on Hubble's work in 1929, Edwin Hubble. And there's a series of galaxies on the left from top to bottom, nearby to distant, going out at the bottom billions of light years. And on the right are their spectra. Now, the spectra look complicated. The discrete lines across the top and bottom of each spectral image, ignore those. That's just calibration put on in the laboratory. What you really want to look at is the band in the middle of each image. That's the collective light of the stars in a galaxy spread out according to wavelength or color. Blue on the left, red on the right. You say, well, it doesn't look red, doesn't look blue. It's a black and white image. But I know it's red on the right and blue on the left. So you'll have to take my word. If you look at the top one, you'll see two little dark bands marked H and K. And astronomers recognize those immediately. They occur in the violet part of the spectrum or the blue part of the spectrum, and they're due to calcium. And they're almost ubiquitous in stars. And as you go down to more distant galaxies, you'll notice that those two little dark lines, the so-called calcium H and K lines, shifted farther and farther and farther to the red, which, according to the Doppler effect, means that that galaxy is moving away from us. In the bottom case, at a speed of 61,000 kilometers per second, due to the expansion of the universe. Okay, so Hubble published this result, and he wasn't the only one who collected this data, but he got all the credit, at least in the popular explanation of this. And so the inference is the following, is that galaxies are moving apart, all moving away from one another. In this diagram, which is a little slice of the universe at the top, time is going up. So let's imagine time going back. Go back in time, galaxies were closer together. And there would have been a time in the finite past when everything was close together. And we would have called that event the Big Bang. Okay, that would imply that the early universe was very, very hot at early times. We can even try to calculate when that time was, and we'll get to that pretty soon. So that very hot early universe would have given off an enormous amount of light because it was so hot, had such high temperatures. And that light should still pervade the universe today. Now, Hubble announced this discovery in the late 1920s, but in 1915, Einstein published the general theory of relativity. And through a long series of theoretical investigations, it became understood that that theory of relativity, that's Einstein's theory of gravity that supersedes Newton's, that we now accept as basically the best description we have of gravity. It came to be understood that, in fact, this can lead to an expanding universe. Okay, but it took a while for that awareness to happen. Well, if this is correct, if the Big Bang theory is correct, the universe should be pervaded by light left over from the Big Bang. And that light was found in 1965 by Arno Penzias and Bob Wilson. Arno Penzias is on the right, Wilson on the left. They worked for Bell Labs, a fairly practical-oriented organization. And they used this rather odd-looking radio telescope to detect the backgrounds of radio waves that are in the sky. Obviously, something you need to understand if you're putting together a microwave-based long-distance telephone system. And what they found out was that the sky has an ever-present emission in microwave at the same intensity in every direction in the sky. They had no idea why, but word got to them that, in fact, this was a prediction of the Big Bang theory, so they immediately published. And of course, this led to a Nobel Prize because this confirmed, was the first step anyway, toward confirming the Big Bang model. Okay. So it was around that time that people accepted the Big Bang description as being basically correct. Now, if you look at this diagram, you'll notice that the galaxies are getting farther and farther apart, but people started asking, well, wouldn't the self-gravity of the universe tend to slow down the expansion. Gravity is thought to be a universally attractive force. And so wouldn't we expect that the rate at which galaxies are moving apart should be slowing down with time simply because gravity is pulling back? All the galaxies in the universe tend to attract all the other galaxies, and the expansion should be slowing down. And in theoretical models, there was even a parameter for this that was put in. That was called the deceleration parameter, meaning the universe should be decelerating. And people started looking for that. That process took decades. But eventually it was realized that a certain specific kind of supernova always tends to give off about the same amount of light. And if you can use the amount of light you receive to gauge the distance, you can test this hypothesis. So the problem is sort of like this. You go out at night, you see a light on the horizon, and you wonder, well, is that a really intense light at great distance, or is it a dim light close by? So you get out your telescope and you look at it, you see the light, you get focused, and you look at it, you notice you can read something on the light bulb, and it says Sylvania 101. That's kind of what you're doing here, because, it's a 100-watt light bulb. It is, you do your calculations 3 miles away. It's the light bulb in that guy's barn over in the next field or something like that. And so astronomers, two groups of astronomers competing with one another, started searching for these supernovae in other galaxies. Well, these are rare events, so you have to search hundreds of galaxies every night and compare the image from one night to the next. You invent robot telescopes that do this on their own automatically, that open up the dome and just start searching. They don't find all the effort and tedium. And so you start to find supernovae. You look how bright they appear, and then you calculate their distances. And the two groups, working in competition, in the end came up with the same answer. Now, here's one of the few graphs I want to show.
Sorry,
That's
Scott's
all right.
having issues upstairs with that.
That's all right. So imagine a supernova at a distance of 8,000. Don't worry about the units. You needn't get bogged down in that. But if you have a supernova at a distance of 8,000 that you've determined by the Sylvania light bulb method, and you go over here, the data says that it has a certain redshift, which is a measure of how fast it's receding. But what you would have predicted were there no change in velocity would be the green line. But before you get to the green line, you notice that those galaxies are receding at speeds that are lower than predicted. So in the past, galaxies were moving slower than they are now. What? We thought it was the other way around. We thought they would have been moving faster in the past and slower now. But in fact, it's not that at all. They're moving faster now and slower in the past. And so these two groups, they went into sort of an internal frenzy because each group thought they got it wrong and that the other group probably did it right. But in fact, they both got it right, and they both got this surprising answer. So the universe is accelerating, and because we don't understand it, the best next thing is give it a name. And it was called dark energy. Dark energy is the thing that is suggested to be causing the acceleration. The idea being that dark energy is something that exists in the universe that we really don't fully understand, that creates repulsive gravity and makes itself felt over huge scales. But we don't know what it is. So we have a pretty good idea of the breakdown between ordinary matter. Less than 5% of the universe is ordinary matter. Dark matter, about 26, 27%. All the rest is this strange dark energy. We don't know what dark matter is. We have not yet detected the form of dark matter, and we really don't have a clue as to what dark energy is. So astronomy is not on the verge of tying all the loose ends together by any means. In fact, everything we've done since Galileo studying planets and moons and stars and galaxies and nebulae, white dwarfs, neutron stars, all that spiral galaxies, elliptical galaxies. All of that effort is about that 5%. There's still 95% we don't understand. So we have a long way to go, which I think makes it exciting. Okay, well, as I said, Penzias and Wilson set the whole thing off when they discovered the cosmic microwave background radiation. And this was followed up by a series of spacecraft investigations, because astronomers knew when Penzias and Wilson made that discovery, there should be in the cosmic microwave background little teeny tiny lumps, because how did galaxies form? In other words, some regions must have initially been slightly denser than others. And those slightly overdense regions would attract in material, form stars and form galaxies. If it was completely uniform way back then, it would be uniform now, and it's manifestly not. The universe is extremely lumpy. So the lumps we have grew from small lumps, but they were very small. So this is one of 3 spacecraft that made all sky images that mapped the entire sky in the cosmic microwave background. This was called the Planck satellite, launched by the European Space Agency. And it mapped the entire sky, and here's the result. And this shows lumps in the cosmic microwave background, grossly exaggerated. If they were shown to scale, it'd be so uniform you couldn't see anything. But the bright spots, the red spots, are a little brighter than the blue spots. And the variation in this map is actually only 1 part in about 100,000. So this is what the universe looked like when it was only 375,000 years old. This is looking back almost to the Big Bang in this image. And the reason we have this image is because when the universe was 375,000 years old, it went from being opaque like that to transparent. So if I look in a direction, I see the wall. Because the wall is opaque, the air is transparent. And so this is looking back to a time when the universe went from being opaque to transparent. Okay. The temperature at that time of the universe was about 3,000 degrees. There is a ton of information in all those little lumps, and it's been thoroughly mathematically analyzed, and it actually supports the hypothesis that the breakdown of matter in the universe is very close to that. Okay, so we have independent evidence. I can't go through it, obviously, that supports that. Okay, so now finally, we can get to the evolution of the universe from the Big Bang forward. So here's a diagram, time, left to right. And there's 2 other dimensions that are spatial, which are kind of perpendicular to left to right. 13.7 billion years ago, the Big Bang. Don't ask me what it was. I don't know. Don't ask me what caused it. You can ask me, but I'll just answer honestly. And I'll say I don't know. Okay. Was there time before the Big Bang? Possibly not, because we have a pretty good description of the gravitation of this from Einstein. And it would imply that both time and space were created in the Big Bang. The Big Bang was a creation of expanding space, and time came out of that as well. I don't even know what that means, but that's what the equations say. Okay. This was not an explosion of some incredibly dense cosmic egg into a pre-existing empty space where a whole bunch of stuff got shot out into a pre-existing empty space. This was an explosion of space and time. Okay, so there was a very rapid period that I've said nothing about in the early universe called cosmic inflation, where the universe expanded from a very small size to a much bigger size. Okay, we have theories of inflation. They seem to be borne out by, oops, I'm going the wrong way. they seem to be borne out by this. This actually supports the idea that there was inflation. And then the universe began a normal expansion. By the way, there is no complete workable theory of inflation. We think it happened, but we don't know the details. And it does have its problems. So the early universe was very hot, very opaque. It was synthesizing elements just like the interior of a star. We'll say a little bit about that. And then we come to this point, 375,000 years after the Big Bang. Okay. And that's what we see when we look back. We can actually see the fireball in that previous image. And by the way, that weird oval shape represents the entire sky, the way you sometimes see the Earth, the entire surface of the Earth mapped onto a shape like that. Well, after the universe became transparent, it was just matter. Stars hadn't formed yet. And so there's a period of time, the length of which we don't know, called the cosmic dark ages. And stars eventually started to form. And then galaxies started to form from those stars. And so a big purpose of the Webb telescope is to look in the period of several 100 million years after the Big Bang to try to understand how stars formed at that time and how they were assembled into galaxies. And we're just beginning to understand that. Now, the Earth didn't come along until pretty far right in this diagram, 4.9 billion years into our past. Okay, so here's a Webb telescope image. It's one we've actually seen before. And for a lot of astronomers, the most interesting things in these images are the little bitty, teeny tiny dots, because those are galaxies at great distance. Those are galaxies very far back in time. And here's several of them, 4 of them. And if you look at the times from top to bottom, they're like 11.3 billion years in the past. 12.6, 13.0, 13.1 billion years in the past. So we see these little tiny specks that are the earliest galaxies. On the right are the spectra, and there's emission at very specific wavelengths that are particular to hydrogen and actually oxygen. So there'd already been some stars to form the oxygen. And they are shifted progressively to the right, to long wavelengths. That's why the Webb telescope operates in the infrared, because all the visible light wavelengths have been shifted way off into the infrared part of the spectrum. Here's another Webb image, 2 of them, and 2 objects. Number 1 on the left, in the left panel, and you can see it blown up there. And it looks like an amazingly well-developed, but very small spiral galaxy. Okay, its light has been shifted by a factor of 10.5. So the wavelengths are over 10 times longer. And let's see, I worked out the distance. That object, as we see it there, existed 450 million years after the Big Bang. Number 2, it's the little red dot in the middle, not the other stuff, but just the little red dot in the middle of the panel is a galaxy as it appeared about 350 million years after the Big Bang. Okay, so what is coming out of this is that galaxies seem to form, stars seem to form, galaxies seem to form from them quicker than anybody expected. Well, up to now, all we had was sort of theoretical expectations of how this process went. And obviously those theoretical expectations are off base. Okay, by the way, that galaxy in the bottom panel, number 2, 350 million years after the Big Bang, is now, let's see, about 33 billion light years away from us now, because since we saw it, the universe has been expanding, and the expansion has been accelerating, and we've been separating from it. And so now it's 33 billion light years away. You can't even see it the way it looks now. You can only see it the way it looked back then. So I promised Jeff that I would finish this with the chemicals that he needs, the elements that he needs to tell us, impossible job, difficult job, to tell us how life may have began on the earth. So here is the periodic table of the elements. The Big Bang was hot enough to fuse hydrogen into helium. Helium is a little off to the right. You see just a little bit of it. It's blue. Blue means formed in the Big Bang. And the calculations would lead us to expect that the universe from the Big Bang forward would be about 28% helium. And that's about what we get. But look at all the other elements. They were formed pretty much in stars. Now, the Big Bang was fast. It was only hot enough to synthesize elements for about 15 minutes. And then it expanded so fast it cooled and it cut off that process. So the process only got from hydrogen to helium. It took stars to make the carbon and all the other things. And in fact, we're now learning that collisions between neutron stars may form elements like Ag, number 47, silver, and Au, number 79, gold. That stuff may have been formed in collisions between neutron stars. So that's where your jewelry, parts of your jewelry may have come from. Okay, so I promised Jeff I'd give him dead planets full of lots of elements, and the job is to try to explain how that led to the formation of life. And I'll leave it at that and entertain questions. Anybody got anything? Yeah.
I know I'm thinking my mind, I'm imagining the universe, which is hard to do. The scientists think there's a barrier. Will it keep expanding forever and dissipate, or is there a barrier?
We don't know. I don't know. The question is, will the acceleration continue on forever? There are scenarios where the acceleration could become so great, it'll start to rip galaxies apart, rip stars apart, rip planets apart, rip molecules apart, rip elementary particles apart, start to shred space itself. So I have no idea. Because first we need to understand the acceleration, and we're a long way from that. Yes.
Okay, I'm going to ask a question from a third grade perspective. When you said the universe went from opaque to transparent, is that because the particles were expanding and getting, like gas dissipating?
Pretty much. What really happened was that the hydrogen in the early universe was initially ionized because it was so hot. So the electrons were free of the protons, and electrons scatter light like crazy. And so the electrons would have meant that any light propagating would have been deflected repeatedly. So it couldn't travel a straight path. And then when the universe dropped to 3,000 degrees, it was cool enough for the electrons to combine with protons, make hydrogen atoms, which are largely transparent. So that's the elaboration on what you just suggested, which is correct.
I have one more question.
Yes.
Since I like Star Trek and science fiction. Can there be other universes?
Oh, yeah. I don't know. I mean, some physicists suggest this, but I really don't know. And I'd be very worried about whether we could ever detect their existence. And if we can, great. But if we can't, then, it's not science, because it has to be at least falsifiable. So there are arguments why there could be other universes. I find them not terribly persuasive, but other people do. So I'm being completely candid. I have no idea. Sorry.
Well, that's a good answer. Talk about the universe, that's a good answer.
Maybe I'm just not imaginative enough. I don't know.
Jane Woodside has her finger up, but she's muted.
Oh. Jane.
You know, one of the things I didn't realize until recently is that we didn't know there were other galaxies till the early 20th century.
That's right.
No idea.
We thought they were clouds of gas and dust in our own galaxy. We called them nebulae, but they turned out to be separate galaxies. And it used to be in the early 20th century, it was thought that our galaxy was the whole deal. Well, there's a trillion galaxies in the observable universe. So that view has radically changed.
So our place in the universe is becoming increasingly small.
Yeah, it's getting smaller and smaller as a proportion of the overall thing. And then, as Gary suggests, if there are more universes, well, then our universe may become a very small part of it.
Yeah.
Yes, somebody.
Brian.
I just wanted to share a favorite quote of mine and make an observation. The quote is, "We plow the dust of stars blown about us by the wind and drink the universe in a glass of rain." Just let that land for a minute.
Yeah.
And then
Because, no, go ahead.
the observation is, in this group, we talk a lot about unknowing, or the notion of that to appreciate God, the divine, that we must truly appreciate. We have to recognize that what we don't know, and that we can never know, and that it's like, if God is really God, there should be a whole lot of stuff that you can never understand. And that pie chart you had with the dark matter is basically the same observation. That's all I want to say.
Yeah, there's a whole lot of stuff we don't understand. Of course, astronomers and physicists are working very hard to understand it, but either that or they want to get that Nobel Prize. Any other questions? And about your quote, also, it's very important to recognize that the soil you plow is made of silicon, magnesium, and all of these elements were synthesized inside stars. And the water you drink has hydrogen from the Big Bang and oxygen from synthesis inside stars that was blown out into space from those stars.
Likewise, the composition of our bodies.
Oh, yeah. All that carbon. I mean, that one element, which has such a versatile chemistry, it's amazing to me. It all hinges on carbon. Jeff will explain that. He understands it far better than I do. And carbon, it's all formed in red giant stars.
What I get from all of this is we live in a magnificent mystery.
Mm-hmm.
Yeah. And we're very tiny and significant.
There was a time in 19th century after Newton and Maxwell after the laws of electromagnetism and basic motion had been worked out, when physicists thought, okay, we've got it all figured out. Now it's just a matter of the details. And of course, the devil is in the details. Maybe I got that wrong. Maybe God is in the details. But of course, that threw everything off course. And there was a great deal that was not understood. So hubris is the enemy of all of this. Well, it's about time.
Yeah.
Under upstairs. So I look forward to.
Thank you so much for doing
Well,
this.
really
Appreciate it.
That was fabulous, Brian. Thank you for both presentations.
That's great. Really great.
Uh-huh.
Okay.
All right. Well, good to see you all.
Oh, my meteorite.
Yeah.
Yes. Okay.
Well, probably the hunters.
Was that a bid?
Pretty cool, though. Amazing how heavy.
That's the thing, yeah. Wow, it's a mind blower.
I know, it's just, you know,
Wow.
I don't really know any more than I did. It is.
It is.
Is it pure iron or is there?
There's other, it's not pure.
Sure, that's
Probably the second most abundant element in there is nickel.
I was gonna say, yeah.
you, dear.
Right next to iron on the periodic.
I say I have this.
Yeah.
So.
Is this magnetic?
Right.
Sure.
Is it magnetic? Yeah.
Yeah, I could pick it up.
Oh, cool.
Yeah.
It is. Just to hold it, I mean, you know, and know how old it is.
Imagine.
Yeah, yeah. You know, coming from Connecticut, we have Yale and Peabody Museum, and they have lots, you know, yeah.
Right.
Which always fascinated me, you know.
Oh, yeah.
Anyway, she came out.
Yeah. And it seems like the past, so there's been a whole lot of asteroids coming through.
They get a lot of attention.
Yeah.
I don't.
It's true.
Control, but media seems, once they get on.
Oh, yeah. And I suppose a lot of them, you know, they're in populous areas that, you know, people would see them, you know, as opposed to they're all the time, but.
I was trying to see.
My wife and I saw one.
I was in California.
Where'd she go? I was driving through
Yeah.
near the center of my town and there was our football field. And it could have been a satellite debris or something, but. And I thought it was gonna hit it. I mean, it fizzled right over the football field. It was pretty cool to see though.
Oh, yeah. My son was walking around in